Hello friends, I am Dr. Manisha, Assistant Professor from KVN Naik College, Nasik. Today we will study lens maker's formula from geometrical optics. In simple theory of the formation of image and in the derivation of lens formula, it was assumed that the light rays makes small angles with the principal axis. Second, the aperture of the lens is small. Third, a point object gives a point image. Today we'll see refraction through the thin lens. Consider the small spherical portion of the spherical surface APB, which is separating the two media of refractive indices mu1 and mu2. O is the point object placed on the principal axis. It incident on this curved surface at 2 points, at point P and at point D. OP and OD are the rays of incident. OP is incident normally on this curved surface APB, and after refraction it travels along PC without deviation. OD is the ray of incident obliquely on this curved surface APB. After refraction it bends towards normal and it meets at point I. DI and PI, these are the two refracted rays, and meets at point I. So I is the real image of this point object O. I is the angle of incidence and R is the angle of refraction. Let I and R be small. Alpha is the angle made by ray OD with principal axis. Beta is the angle made by ray DC with principal axis, and gamma is the angle made by DI with principal axis. Now, as D is close to point P, so tan of alpha is equal to dP upon PI, OP. Tan beta is equal to dP upon PC, and tan gamma is equal to dP upon PI. Now, in triangle ODC, I is the exterior angle. So, I is equal to alpha plus beta. In triangle DCI, beta is the exterior angle. So, beta is equal to R plus gamma. From Snell's law, mu2 upon mu1 is equal to sin I upon sin R. Mu1 and mu2 are the refractive indices, and I is angle of incidence, R is angle of reflection. As I and R are small, so we can write sin I as I and sin R as R. So mu2 upon mu1 is equal to I upon R. Now, after cross multiplication, we will get it as mu1I is equal to mu2I. Now, from equation 1, 2 and 3, after substituting the values of I and R, we can write mu1 into alpha plus beta is equal to mu2 into beta minus gamma, which is the value of R, and alpha plus beta is the value of I. So, after opening the bracket, we can write mu1 alpha plus mu1 beta is equal to mu2 beta minus mu2 gamma. Now, rearranging the terms, we can write mu1 alpha plus mu2 gamma is equal to mu2 beta minus mu1 beta. So, we can write mu2 minus mu1 into beta. Now, substituting the values of alpha, gamma and beta in this equation, we can write, instead of alpha we can write dP upon PO, instead of gamma we can write dP upon PI, and instead of beta we can write dP upon PC. So, dP is common in all the terms, so it will get cancelled, and we can write mu1 upon PO plus mu2 upon PI is equal to mu2 minus mu1 upon PC. Now, as the incident rays comes from left to right, we choose this direction as the positive direction of the axis. Therefore, U is negative, whereas V and R are positive. Now substitute the value of PO as minus U Pi as plus V and Pc as plus R. So we can write mu1 upon minus U plus mu2 upon V is equal to mu2 minus mu1 upon R. Now this equation represents the general equation for refraction at the spherical surface. If the first medium is air and the second medium is refractive index mu, then we can write this equation as mu upon V minus 1 upon U is equal to mu minus 1 upon R. Now we'll see lens-maker's formula for thin convex lens. Consider the thin convex lens of refractive index mu2, which separates the medium of refractive indices mu1 on its two sides. Let R1 and R2 be the radii of curvature of the two coaxial spherical surfaces. A point object O is kept on the principal axis at a distance of U from the lens. Final image of object is formed at I due to the refraction of rays at spherical surfaces first and second. Now refraction at surface first. If the surface second were absent, an image I dash is formed by the refraction at the first surface, and let its distance from the pole of the first surface be V dash, that is P1 I dash is equal to V dash. Now using the relation between UV and R at a single curve, we can write mu2 upon V dash minus mu1 upon U is equal to mu2 minus mu1 upon R1. Now refraction at the second surface. Due to the presence of the second surface, the rays pass from the medium of refractive index mu2 to the surrounding of refractive index mu1. Thus, image I dash will be regarded as virtual object for the surface second, and its real image is formed at I in the refractive index mu1. Using the relation between UV and R at the single curved surface, we can write mu1 upon V minus mu2 upon V dash is equal to mu1 minus mu2 upon R2. In this case, the rays are passing from the medium of refractive index mu2 to the medium of refractive index mu1. So adding the equation 1 and 2, we can write mu1 upon V minus mu1 upon U is equal to mu2 minus mu1 into 1 upon R1 minus 1 upon R2. Dividing throughout the equation by mu1, we can write 1 upon V minus 1 upon U is equal to mu2 minus mu1 mu2 upon mu1 minus 1 into 1 upon R1 minus 1 upon R2. If the length of refractive index mu is replaced in air medium of refractive index mu1 is equal to 1, then the above equation will be 1 upon V minus 1 upon U is equal to mu minus 1 into 1 upon R1 minus 1 upon R2. Thus, equation 4 is called as lens-maker's formula. According to the definition of focal length, when the object is at infinite distance from the lens, its image is formed at focus. So, instead of writing 1 upon V minus 1 upon U, we can write 1 upon F is equal to mu minus 1 into 1 upon R1 minus 1 upon R2. This equation can produce lens of desired focal length from the glass or any other transparent medium of given refractive index by choosing the proper radii of spherical surface R1 and R2. It must be noted that this equation holds true only for the paraxial and for thin lenses only. Thank you.